This is a short presentation on implants and instruments. Some specialised instruments are required to perform basic fracture repairs, but not the extensive inventory needed for applying plates, screws and complex external fixation devices. Here we'll cover the implants needed to carry out the procedures we've been discussing, along with any special instrumentation needed to make this possible. Arthrodesis wires come in a range of lengths and diameters. For using to cross-pin physial fractures or in tension band repairs of avulsion fractures, 12.5 cm length and diameters from 0.9 to 2 mm will cover most options. These pins have a trocar tip at either end, and as mentioned before, don't throw out the piece of pin that you cut off. It can be reused for your next case. These pins don't have threads. K-wires are basically the same, although they've got a trocar tip at one end and a flatter bayonet tip at the other. I haven't used K-wires for years, preferring the versatility of arthrodesis wires, but either will do for the surgeries that we're discussing. Unless the bone is incredibly soft, these need to be driven in with a low-speed drill for accuracy. And remember to keep the distance between the drill and the bone, that is the working length of the pin, short, otherwise the pin will bend too much. We do not need to pre-drill arthrodesis wires, just insert them directly into the bone. Intramedullary pins are similar, coming in various diameters from 1.6 up to 6.5 mm, with trocar tips at either end. With intramedullary pins, we often need the trocar tip at both ends when retrograde pinning, but a cut-off section with only one trocar tip can still be reused in direct pinning or as a connecting bar for an ESF device. IM pins also come with negative threaded trocar tips, which provide better resistance to pulling out of metaphyseal bone. IM pins are more accurately inserted using a low-speed orthopedic drill, giving more control over entry and exit points, although in some situations the Jacobs chuck may be easier to use. If the IM pin is not being tied into an external skeletal fixator, then you'll need bolt cutters to cut it off as close to the bone as possible. Now, we mentioned earlier about the countersinking technique. This will allow the pin to be seated flush with the bone surface, and it can be an advantage in that it causes a lot less soft tissue trauma, but it can make the IM pin very difficult to retrieve if you ever need to. Orthopedic or cerclage wire usually comes in rolls of varying diameter from 0.2 to 1.5 mm, and these rolls are usually about 10 meters long. The whole roll is sterilised, and you can then cut off the appropriate length during surgery. If you pre-cut the wire and sterilise before surgery, you'll have a long wait for another piece if you break or drop the piece you're working with. I'll often just keep 3 thicknesses that cover most situations, for example 0.4, 0.8 and 1.1 mm diameters. Remember that in tension band repairs it's the wire, not the pins, that do the work. So if in any doubt, select a thicker wire. Here we've got orthopedic wire used as cerclage wire, and here on the right it's being used in the tension band repair of an avulsion fracture. ESF pins come in various sizes. The ones we have discussed and will be likely to use to support an IM pin repair are end thread pins. Mid-thread pins are used in Type 2 ESF constructs. ESF pins can either have smooth trocar tips, negative thread tips, or positive thread tips. Smooth trocar tips are the cheapest, but they've got very little resistance to pull out if they're placed perpendicular to the bone, and so they need to be inserted at an angle of approximately 70 degrees to the long axis of the bone to be successful. You can use cut-off sections of the smaller IM pins to use as smooth trocar tipped ESF pins. Threaded ESF pins are much preferable since they're more versatile, not having to be inserted at a certain angle in the bone in order to be effective. And the thread can be cut into the shaft with negative pins, or it can stand proud of the shaft with positive pins. Now, I prefer positive threaded pins, but they're a little more expensive and they require a larger diameter hole to be pre-drilled. Positive profile pins have a better pull-out resistance than negative profile pins, which in turn have a better pull-out resistance than smooth pins. One thing to remember with negative thread pins is that there is a weak point where the threaded portion starts, and so this must be protected by placing it within the medullary canal of the bone when using these. With positive threaded pins, it doesn't matter if the thread shank junction lies out with the medullary cavity. ESF pin diameters come in a large range, varying from 1.1 up to 4 mm diameter, and which thickness of pin is used will dictate normally which sizes of clamp and connecting bars are used. And as I'll discuss in a moment, we're not going to cover the vast inventory of different clamp sizes and connecting bar types, but rather concentrate on what we can achieve using epoxy putty as our clamp bar substitute. Whilst it's not as predictable as using a set clamp bar system, it's massively cheaper and it gives us significant versatility in where and what size of pins we place. In general, 2, 3 and 4 mm diameter threaded pins will cover most options, although it is worth having some smaller diameter ones too for kittens and small puppies, for example 1.6 mm diameter. You need to pre-drill the bone when using positive thread ESF pins, whereas with thinner negative thread pins and smooth trocar pins, this may not be necessary. External skeletal fixation systems can be complicated, with the different thickness of pins often dictating to a degree what size of clamp and connecting bar combination is used. Modern clamps can often accept varying pin sizes, which helps. There's many different systems out there, but we're going to discuss none of them and instead concentrate on substituting expensive but reusable clamps with epoxy putty. This will restrict our use of external skeletal fixation to all but the simplest of applications, but we'll need to concentrate on what is achievable in our circumstances. Epoxy putty. This substance is relatively cheap and it usually comes in sticks with a pre-measured catalyst in the centre. Simply cut off the amount required from the stick and mix it well. The product stiffens in 5 minutes and it cures within an hour. It can be used to attach the ends of the ESF pins to a connecting bar, or in smaller patients it can substitute for the bar itself. It helps to make notches in the pin ends with bolt cutters to facilitate adherence. Using putty rather than clamps also allows maximum versatility when combining different sized ESF pins with different sized connecting bars. You're not confined by the restraints of clamp size. The main disadvantage over clamps and connecting bars is that once a putty is cured, there is no option to make any adjustments. Once a fracture is in satisfactory reduction, apply the putty to the pin ends and connecting bar and wait for it to cure. Epoxy resin can cause skin reaction, so it's advisable to wear nitrile gloves if you can. I'm not sure if latex gloves act as a chemical barrier here. The friend of every orthopaedic surgeon is the drill, and without this, even the most basic of fracture repairs will be hard to carry out. If you're doing a lot of orthopaedic work and using compression plates etc. on a regular basis, then air-driven drills and handpieces are the way to go. They, along with the air hoses, can be autoclaved whole and so provide perfect sterility in the operating field. These unfortunately are expensive and require compressed, high-quality filtered medical air supplies to operate. In the human field at the moment, there's a renewed interest in completely autoclavable battery-operated systems. For many years I used battery-operated drills with autoclavable cloth drill shrouds, and while not a sterile unit, they provide a good alternative. This is a standard variable speed Bosch drill, which has been adapted to allow the attachment of sterile chucks and chuck extensions. And although the drill can't be sterilised, the chucks can, and so when wrapped in the sterile drill shroud, the unit is sterile. I often wrap a length of sterile bandage around the end here where the chuck comes out to make sure the drill shroud doesn't slide back. These drills, they've often got torque, control and hammer options, but the main function we're looking for is that they've got a variable speed control using the trigger and that they've got a reverse function. This one operates at an RPM of about 400 to 1300, which is fine for drilling holes in bone. When drilling, start slowly until the drill bit starts to seat in the bone and then increase the speed. If the drill bit keeps sliding off the bone, then use a scalpel to create a small defect where you want the hole and use this to secure the tip of the drill bit. A simple but important point is to get into the habit of using sterile saline to lavage or flush the drill bit or implant as you insert it to reduce the risk of causing heat necrosis in the bone. I generally lavage everything, Even a tiny amount of heat necrosis will result in bone dieback, and that means that your implant, whether it's a screw or arthrodesis wire or IM pin, will no longer grip or be seated tightly in the bone. Certain implants, like small arthrodesis wires, you should be able to insert directly into the bone. Larger diameter implants, for example 2 mm and over, you'll need to pre-drill first with a drill bit narrower than the implant to avoid risking iatrogenic fracture. In general, when placing ESF pins, I aim for a drill bit about 10% narrower than the diameter of the pin itself. Just eyeball or look at the drill bit and the threaded pin and make sure that the drill bit is thinner than the section of the pin that is threaded or the shaft of the pin. Remember that positive profile pins have threads standing proud of the pin shaft, whereas negative profile pins have the thread cut into the pin shaft. The rules are flexible though. In very young soft metaphyseal bone, pre-drilling is not often needed with thinner diameter pins, whereas in hard, older diaphyseal bone that is less plastic or malleable and more prone to fracture, I would definitely pre-drill. The type of variable speed orthopedic drill that I've just shown in the previous slide will have a stated RPM range. In that case it was 400 to 1300 RPM, but it can be operated at as low a speed as you require from 0 up to 400 as well. The maximum rating of these drills is more than enough for drilling bone, but it's the ability to use them at very low speeds that's important. Have a range of drill bits with diameters from 1.1 to 4.5 mm. And drill bits are reusable depending on whether soft, which allow 10 uses, or hard drill bits are chosen. A drill sleeve can also be handy to have, and this device has serrated teeth at the end of a metal sleeve that allows it to grip the bone and prevent the drill bit slipping. The metal sleeve protects the surrounding soft tissues while you drill the bone. General surgical instruments which are useful when carrying out fracture repairs include Gelpi self-retaining retractors, and I'll often use 2 pairs at the same time. These basically act as another pair of hands, and I'll use these in almost every orthopedic surgery I undertake. The other form of retractor I find comes in handy is the simple Hohmann retractor. Of the vast array of specific orthopedic instruments out there, without a doubt having at least one pair of pointed fragment reduction forceps should be in your armoury. Again, these act as a separate pair of hands and allow the fracture to be held securely in reduction while you place your implants. Be careful not to use them too close to the fracture edges or to close them too tightly, or you may fracture the bone. Close the jaws with the least amount of pressure necessary to hold the bone ends in place, and don't be tempted to give them that one extra click. Here we have a pair of pointed fragment reduction forceps holding a humeral fracture in reduction, and here we have a pair of Gelpi self-retaining retractors exposing the fracture site. A periosteal elevator is handy to have for gently removing soft tissue from bone in order to place implants. Bear in mind though that in the types of fracture repair we will be doing, we're aiming for secondary bony healing, and preserving the soft tissue envelope and blood supply to the bone is important. This type of periosteal elevator has a sharp edge with one flat side and one convex curved side to separate soft tissue from bone as it is advanced. The Jacobs hand chuck and key. This is used when inserting IM pins if you're not using a drill. When using a hand chuck, it's important to operate it with axial rotation of the wrist to reduce pin wobble and the creation of an oval hole in the bone. Drill insertion of IM pins under low speed is much more accurate from this perspective. If I retrograde pin, as I'm doing here, I will sometimes use the hand chuck, but if a normal grade pin, I find the drill much easier. I will always use the drill at low speed, never the hand chuck, when I'm inserting arthrodesis wires or external skeletal fixation pins. The K-wire bender. It's basically a metal tube that slides over the arthrodesis or K-wire and makes it easier to create a bend right at the bone surface before cutting the pin. It's sometimes easier to bend in one direction to get the best result, then remove the K-wire bender, rotate the pin around and cut it. An example of this being the tibial tuberosity. Be careful using the K-wire bender in soft bone such as epiphyseal fractures in young puppies, since the action of bending the pin may distort the hole where the pin enters the bone and therefore reduce stability. In this situation, just cut the wire flush with the bone. On the right here is a proximal physial fracture of the tibia with associated tuberosity avulsion fracture. The tuberosity is a tension band repair, and we have an additional arthrodesis wire here to secure the epiphysis. In this image, the K-wire bender is being used to bend down the end of the arthrodesis wire so that it does not irritate the soft tissues of the joint. Wire twister cutters, essential for tensioning cerclage wire when using either in oblique fracture repairs or tension band repairs. This instrument has a dual purpose of both twisting and cutting the wire. They can also be used to cut arthrodesis wires as long as the wire diameter does not exceed the limit of the instrument. Bolt cutters. Fine wire cutters will be necessary to cut arthrodesis wires flush with the bone surface, and more heavy-duty bolt cutters like these to cut intermedullary pins, ESF pins and connecting bars to length.